Okay, we start the idea of developing curvature with the question whether a big circle has more or less curvature than a smaller. And the first answer I got was, well, the big one has less curvature, okay? And then I just said, okay, intuitively, if you're driving at the same speed along a big circle or a little circle, which one has a lower limit on your speed, for example? You know, what happens? And obviously, if you're turning a lot faster at a speed, you're eventually going to spin out on the small circle before you would at the same speed on the bigger circle, okay? So, it's less, right? Okay? So, I'm going to define the curvature of a circle and we use this kappa symbol, 1 over its radius, reciprocal of radius, okay? So once I figure out the curvature of this path, I can take the reciprocal of that, and I know the radius of my osculating circle. I know the plane it's in, so all I got to do is move along the normal vector in the direction, well, in the direction of the normal vector, a distance equal to the radius, and I'm at the center. Okay? And of course it's a matter of writing the equation of the circle, which is a little bit of an issue, but not too bad. Make sense? Okay, so that's our definition of curvature. Now, the curvature of a curve I'm going to just say the curvature is intuitively the rate of at which your direction changes with respect to distance along the arc. Now, we haven't talked about the arc length parameter because the way it's done in your book is fairly straightforward. I'm going to let you ponder that a little bit, and if we need to, we'll reconcile that next time, okay? But curvature is the rate at which direction changes with respect to distance along the arc, right? Okay? So, moving at speed v around a circle of radius r, make it a big R, at what rate does your direction change with respect to distance? I'll say with respect to t, okay? Because that's a straightforward answer. And then with respect to s, which is distance along the arc. What do you think?